Good evening and good morning. Let us read today about low-budget muon sources. Abstract. Generation of muon beams with protons on a current-carrying target followed by a lithium lens and a quadrupole decay channel is considered. A 8 gigaelectron-volt proton beam from the Fermilab booster is used to provide a muon beam for the MuCool experiment for ionization cooling demonstration. The proposed scheme can be used to create muon beams with a fraction of a 1 gigaelectron-volt proton beam of the spallation neutron source. Monte Carlo simulations of the entire system are performed. For both cases, optimization of the target and matching lithium lens is done. It is shown that such a set followed by an inexpensive decay channel based on quadrupole magnets with and without RF cavities provides a rather intense bunched muon beam. 1. Introduction. To achieve adequate parameters of a neutrino factory based on a muon storage ring, it is necessary to produce and collect large numbers of muons. A baseline scheme is based on 16 or 24 gigaelectron proton beam IMPing on a tiled carbon or mercury jet target in a high-field solenoid 20 Tesla, about 1 meter long, aperture radius about 7.5 centimeters, followed by a matching section and a solenoid decay channel of about 1.25 Tesla, 50 to 100 meters in length, and about a radius of about 30 centimeters, which collects muons resulting from pion decay. In this paper, we are exploring a drastically cheaper scheme that can still produce a muon beam usable for entry-level neutrino factory, other applications with intense muon beams, and for the MuCool experiment to study ionization cooling. The scheme starts with the existing 8 gigaelectron Fermilab booster proton beam on a current-carrying target, followed by a low-gradient lithium lens. Pion beam, primarily focused into lens, decays into muons in the decay channel based on also existing quadrupole magnets from the B and L D2 channel. Pion production and capture in the target station, as well as the formation of a bunched muon beam in the decay channel, were simulated with the Mars code. The latter was also performed with an independent specialized Monte Carlo code. A good agreement was found. Therefore, most of the tracking results below were obtained with this fast code. 2. Target station. Layout of the target station is shown in Figure 1, and its parameters are listed in Table 1. The station includes a current-carried target for pion production and collection. Here we have Figure 1, layout of the target station. Protons enters into a target. We have an Li lens or lithium lens, which outputs pions, and the decay channel. Here we have Table 1 with the parameter, symbol, target, and lithium lens. The parameters of the target station that show us the material, length, radius, current, maximum field gradient, and beta function. And there you have it. Okay, so where does this go? The station includes a current carried target for pion production and collection and a lithium lens for matching to the decay channel. Phase rotation of pions or muons is not presumed in the scheme. Therefore, the system is tuned to provide the best condition for pions with momentum, approximately equal to 300 megaelectron volts per coulomb, where pion yield is close to maximum. At 8 gigaelectron volts, a 15 centimeter long copper target provides maximum yield. See Figure 2. The magnetic field gradient inside the target is taken to betatron phase advance 180 degrees, attaining by this the best filling of the transverse phase space by pions with momentum PO. The target radius is taken to get an acceptance of about 0.54 centimeters, which is slightly less than expected acceptance of the decay channel. See below. It follows also from Table 1 that phase advance is about 90 degrees at the lithium lens. At such conditions, the lens provides the optimal matching of Figure 2. Mars calculated pion spectra per interacting proton. At the downstream end of a lithium lens for 8 gigaelectron volt protons on a 15 centimeter copper target and 1 gigaelectron volt protons on a 15 centimeter beryllium target. There you have it. Moving on. So at such conditions, the lens provides the optimal matching of the target with a channel with a beta function of beta channel equaling beta 2 lens over beta tar G, approximately equaling 135 centimeters. The Mars calculations were performed for the 8 gigaelectron volt booster beam with sigma xy equaling 6 millimeters and RMS bunch length sigma z equaling 30 centimeters. Pion spectra at the exit from the lithium lens are shown in Figure 2. The results are also shown for the system with the proton energy reduced to 1 gigaelectron volts S beam, and the copper replaced with beryllium of the same longitudinal and transverse dimensions. We found that for low-energy proton beams, a usage of low-Z materials maximizes the positive pion yield. For a 8 gigaelectron volt proton beam, total number of pions per proton for the lens is 0.119 with the 0.002 muon created already. Pion yield is somewhat less. So there's pion plus and pion negative, and muon plus and muon negative, or should I say anti-pions and anti-muons. However, only at 0.028 pion plus pion plus muon per proton fall into the total energy interval of 280 to 420 megaelectron volts acceptable for subsequent utilization. Transverse phase of these particles is also shown in Figure 3. A central core and halo are seen very distinctly in these plots. Higher energy pions, as well as particles produced in the lens, appear in the halo most probably. The number of pions plus muons in the central core is about 0.02 per proton. Within the radius, less than 8.5 centimeter radius, with the above energy cut. It means that with a careful design of the decay channel, one can get quite intense muon beams at its end. For the considered parameters of a booster beam at 5 times 10 to the 12 ppb triple P at 15 Hz, the peak energy deposition, temperature, and power dissipation of the copper target are quite manageable with an appropriate cooling system. Radiation levels in the target station are quite high, but can be localized within several meters from the target and controlled with a corresponding shielding. 3. Decay channel. A channel with RF and a bunching channel with RF are considered below. Both of them utilize the BNL D2 pion beam line quadrupoles. These quadrupoles have a maximum gradient of about 0.1 Tesla per centimeters, an effective length of 36 centimeters, and an aperture radius of 13.7 centimeters. 3.1. Beam line without RF. This decay channel consists of photocells, each with 2.059 Tesla per centimeter quads, and two 36 centimeter straight sections. The number of cells is 34 in this design, and additionally one lens of the same length, but lower gradient, 0.003 Tesla per centimeter is put at the channel downstream end. It provides alpha x equals alpha y and beta x equals beta y. That is convenient for matching with the following solenoid cooling channel. Total length of the channel is 50.6 meters. Figure 4 shows 3 cells and the matching lens at its downstream end. The channel acceptance of 0.78 centimeters equals 7,800 millimeters by mrad is almost 1.5 times larger than the target station acceptance. The margin is required because the beam emittance increases due to pion decays. Evolution of the beam parameters in decay channel is shown in Figure 5. The upper curve represents sum of pions and muons. A fast decrease at first 1 to 2 meters is explained by loss of pions with PT greater than 30 mega electron volts per coulomb, per C, which are outside the channel acceptance. Slower loss after that testifies that the channel acceptance is not sufficient to save all muons because some of them get large additional transverse momentum at the decay of their parent pions. The number of muons at the end of the channel is 7.8 times 10 to the negative third total, and 24 times 10 to the negative third with the 255 being less than E total and E total being less than 355 mega electron volts intervals. A normalized transverse RMS emittances are 0.53 centimeters and 0.47 centimeters correspondingly. The absolute maximum of the yield is obtained for a 8 meter channel, but it is only slightly higher at 2.5 times 10 to the negative third within the above energy interval. Muon phase space at the end of the decay channel is shown in Figure 6. Beamline 3.2 Beamline with RF puncher. A part of the decay channel destined also for beam punching is prescribed or presented schematically in Figure 7. Oh, Figure 7. There you go. The 118 centimeter long straight sections are included to provide the room for RF cavities. A central 4 meter length long cell has a periodical beta function and can be applied or multiplied as many times as needed. Actually, the channel contains 12 such cells. 2 special doublets at the ends are included to provide the same beta functions for both x and y directions. Total length of the channel is 50.2 meters, that is, almost the same as the previous design. The quadrupole gradient is 0.0404 Tesla per centimeters, except for the first and last lenses where it is 0.0143 Tesla per centimeters. The maximum beta function on this channel, or in this channel rather, is 1.4 times higher compared to the previous one. Therefore, it has smaller acceptance and provides, without RF, 2.6 times less muons than the previous scheme. 14.4 megavolt RF stations, 201.25 megahertz frequency, 96 centimeters long, are placed in the 118 centimeter straight sections. A longitudinal phase space after the bunching is shown in Figure 8. The number of muons in a central bunch is about 0.5 times 10 to the negative third per incident proton. The bunches are formed not very nicely because there's no factors to kill uncaptured muons. Beam bunching in the cooling channel itself seems to be more preferable. The efficiency of using very expensive accelerating systems would be higher in this case. 4. Muon beam at SNS. The scheme proposed above can be used to generate intense muon pion muon beams at the spallation neutron source (SNS). Assume that 10% of its 1 gigaelectron-volt beam is directed into a pion production target. As we found for such a beam, the maximum pion yield at 0.4 gigaelectron-volts per C or coulomb one gets from a 30 centimeter beryllium target. At the end of the channel described above, we get 1.5 times 10 to the negative third muons per incident proton at the kinetic energy of 200 plus or minus 70 megaelectron volts for the 2 megawatt 2 milliamp hours SNS beam of 2.08 times 10 to the 14th ppp, with 10% on the pion production target. One has 4 times 10 to the 10th muons per pulse, or about 2.4 times 10 to the 12th muons per second, i.e. about 10 to the 4th more than the best existing beams. This beam already is ready to be used directly, or after modest cooling, in a muon storage ring as a source of intense V-beams. It can be used for a test facility for a muon collider. There are also numerous research options with such muon beams, including material science and applications. And we get down to number 5, the references, and that's already listed there, but we're not going to read those. But you can have a nice look at these figures from 1 to 4. Again, just by pausing the video if you want, but that's the data for you. I hope you enjoyed this section, ladies and gentlemen. Nice narration here. Cheers.